Hey, hello there. Today's Leetcoding challenge question, it's called the longest duplicated substring. So the definition for a substring is that it's a continuous chunk of characters inside the string, so it's a window inside the string. Duplicated window is basically the same window appeared at the two different positions, at least the two different positions inside the string. So this question is asking us to find the duplicated windows. And among the longest such window, we want to just randomly return one of those is fine. So this is the question. Let's look at the example. The input string is banana. So let's just look at the window size in the increasing order. Let's look at the window size 1. The duplicated window we have will be A and N. A appears 3 times, N appears 2 times. It's easy to look at that. Window size 2, we will have 2 windows that appear more than 1 times. The first one is AN, the second one is NA. We can easily verify that with the input string. The length 3 ones are, there are only one choice now, which is ANA, which is starting at so the ANA is either 1 to 3 or 3 to 5. It appeared twice, so it's duplicated. For length equal to 4, there is no such window. We can just quickly enumerate over all the length 4 windows to see that. We have BANA, that's 0 to 4, 0 to 3, and ANAN, that's 1 to 4, and the last one is NANA, which is from index 2 to index 5. There is no duplicate here, so from length 4 and on, we don't have duplicated substrings. So I guess it's easy to see that if we have a length 3 duplicated window, it's guaranteed that we will have a duplicate in length 2 and length 1, because we can just took 2 windows of ANA and just slice that to be one smaller. Just take the first 2. It's guaranteed that we will have that duplicated among those 2 different windows. So if we have a function that's called FL, so the thing that it will return is a boolean. Do we have duplicated substring of size L? So when we map this function to the range from 1 to the total string size subtracted by 1, the function call result will be true, 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 true until the longest, and after that will be false, 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 false. So this is telling us we can apply binary search to find the longest length. So here FL is true. Just gonna demonstrate that a little bit. From 5, you can do this yourself to verify it's not. Because for 4 it's not possible, then for 5 there's no way it's going to be possible. I think you can easily verify that. So just gonna note down the first thing we noticed by looking at the example. We can apply binary search to find the longest, the largest window size. So that's the first thing we can do. The second thing is how we actually do this duplication check. Through this example, we can see that we basically just kind of have a sliding window inside the string for a fixed size, and just move that window towards right one at a time, one character at a time. For each time, when we move the window to a new position, we hash that the content of the window into a hash set. So if we find the key is already in there, that means we have a duplicate. The time complexity for this naive approach is going to be n multiplied by L, the size of the string multiplied by the length of the window. Because for every window, if we just naively hash that into the hash set, first it takes an order of L time, the window size time, to grab all those characters. Then we have to compute a hash out of it every single time. That's order of L as well. So the total runtime for doing this comparison, this duplication check, is order of n multiplied by L. So combine this with the binary search, it will be ml log of n. So that's the total runtime complexity if I apply binary search on top of this naive duplicate window detection. So since that the window size can grow quite large, and we want this is something we need to run for every binary search call. So we want to have this to be as quick as possible. One thing we can notice that if we roll the window over, the previous window is BANA, the next window is ANAN. The only thing that's changing is the exiting character and the entering character. So we want to do some updates just on those. Primarily just going to be on the character we emitted and the character we introduced. So one thing we can do is to apply the rolling hash method. So how it works is actually quite simple, quite similar to how binary to decimal number conversion works. So let's say that I have a program that has 3 different switches, and so it's on and off. So the state of the program can be on, off, on. So convert that into, if we use 3 different variables to code this state, it will be 1, 0, 1. And at some other time it might be off, on, and on, so it will be 0, 1, 1. One thing that we can compare whether these two state, whether these two, in our string context, it would be whether these two windows are the same. We can do this single position at a time kind of checking. That's essentially what they hash the whole thing, hash the whole string every single time. For every single window, using the naive hash works. It's processing that position by position. But the other thing that we can do is to, for my on and off switch question, it's a binary number. It's a binary number, so we can just convert that into decimal. So this number in decimal will be 4 plus 1, which is 5. And this number, this state, of the 3 different switches is going to be 2 plus 1, that's 3. So instead of comparing these two things, two windows, one position at a time, if we just represent this as integer number, decimal integer number, the only thing that we need to do is to compare their decimal number values. So so that means the hash and checking with the set can be more efficient if we can somehow represent every window as an integer, as a decimal integer. So for in our case, every position here we have 26 different characters. It will be a 26 26-nary digit number to decimal conversion. We can still do that. It's just instead of multiply every position to the 2 to the power of I, we multiply that position by the 26 to the power of I for every i's position inside of the string here. We'll map A to 0, B to 1, Z to 25, things like that. And looking at the position by position, just multiply that integer number to the power 26 power of location. We can convert the window into the decimal. So it's basically polynomials. So that makes the hashing and the lookup faster. But use that representation also help us to do the moving window faster. So let's just illustrate how that works. So for BANA, the first window, it will be something like B is going to be mapped to, let's say that, I'm not sure what number is n. A is 0, B is 1, and n let's just call it 22. I'm not sure. So the convert this to decimal, it will be 1 multiplied by 26 to the 0 power plus 0 multiply 26 to the power of 1 plus we got an n, that's 22 multiplied by 26 to the power of 2, add another 0 multiplied by 26 to the power of 3. So that's if we're converting this whole window to decimal. What if we roll this towards right by 1? It will become a n. So we notice that we have to basically downgrade the power here for every single one of those, except the very first one. The very first one should be gone. So we delete this because the b is no longer there, and we're introducing a new one that is 22 multiplied by 26 to the power of 3. So we divide the whole thing by 26, subtract we subtracted the exiting number to the correct power, divide the whole thing by 26, and add the new entry number multiplied by the correct power. So doing essentially kind of a 3 operations, get rid of 1 by subtracting the numbers multiplied by the power, and divide the whole thing. The second step to downgrade everyone to perform a shift, and introducing a new one. So 3 operations that give us the shifting of the window. So instead of doing n multiplied by l, the window, this duplication, sliding window duplication check with rolling hash will be n multiplied by certain constant instead of l. So that saves time. And I guess another thing to note is that the power can be, when the lens goes larger, we are multiplied by 26 to the very large lens, subtract by 1 kind of a power. The number goes larger and larger. So that's why we want to introduce a modular, big number modular everywhere when we do this window calculation. So that's pretty much it. We're going to reduce the runtime to n log n. Some constant multiplied by n log n. The constant is the time we need to update the window. Log n is from binary search. N is from the rolling hash duplication detection. So that's pretty much how we summarize the how to approach this problem. The detail in the implementation makes this question bump to hard level. The big idea behind this is sort of like medium level, but the runtime check for this question is just very tight. So let's code this thing. We will do a rolling hash, which takes a lens and try to detect do we have a duplication with this window size. So we're gonna start with a hash number 0 and just compute the first window, and then we're gonna in a for loop move that window over to the very end, do the duplication check. For character in, one thing we can do is to speed things up is to first create the character to their integer number kind of mapping, and either look it up every time, which can be slower, or just convert the whole string input into an array of integer, where each position is the integer representation for the character inside the string. So let's just call this D. It's going to be the convert the lowercase letters to their alphabet ordering. So with this, we can just do D up to the first window end, we're gonna do is to multiply this by some power, which is 26, the vocabulary size, plus the newcomer. So the mask is slightly different compared to the example here. The example, the lower position, the more towards the right, the higher the power gets raised. But here, in the actual code, I have the leftmost to be the highest power. But it's not really a big deal. Big deal difference. It's just I think when I multiply the leftmost chunk, the math is a little bit easier. So we're gonna mod this by a big modular number every time we do a calculation. Let's say that it's 2 to the 22. So with this, we basically have our first window now. So I'm just gonna put that into a set as the very first hash we have. So just do a little comment. Initial window. Then there's a sliding window. From the previous window's ending point and on, we want to update the window. So we're gonna do is to subtract the leftmost, the previous leftmost, which is R subtracted by the window size. That thing has to be multiplied by let's just call this PP, which is P to the power of L, because it's the leftmost one. How long the size of the window, that position, the integer number at that position has been raised to the P to the power of L. And we are doing modular everywhere, so that's why put that there. So we have to raise the integer number at that position to that correct power. Because it's exiting, so we subtracted that and adding the new one, and do another modular as well. So this is updating the window, and then we check if this new hash is in the set. If it's in the set, that means the current window we're looking at is a duplicate of a prior one. So we can return the starting position for this window, which is going to be R subtracted by L plus 1. The reason for plus 1 is that we're getting rid of the character at this position, so the new starting position is this one. Otherwise, we'll just add this new window hash to the set. In the end, if we don't find any duplication, we can just return none or false, something like that, indicating that there is no duplication. So this rolling hash function will give us direction to apply binary search. We're going to try the length, window size length from 1 to n minus 1. So that's the lower bound and upper bound. Actually, we are finding, we want to find the largest window size such that we still have a duplication, which is the equivalent to saying that we want to find the smallest window size where we couldn't find any duplication. And in the latter one, we just return the number we find subtracted by 1. So for that reason, I'm gonna go to use that. It's gonna be essentially the it's equivalent. So I'm doing this. First, I get the middle point. Then I want to see if I can find a duplicate. If I can, I will increase my lower bound to be n plus 1. So I want to find the first position where I couldn't find a duplicate. So after this while loop, L-1 is the largest window size, duplicated window size. So we can just run this this window size through this rolling hash one more time to get the starting position for the duplicated window in its second occurrence inside the string. In the end, we will return S from the start position to start plus L-1. That's the window size. L-1 is the longest window size. Yeah, let's just quickly check, do I have problems? Yeah, so that's the code. Let's see if it works. Nope. What do we have? I forgot a column. Nope. Still nope. I'm returning empty string. What's the problem? I see. I think I forgot a multiply of the power here. So let's just comment a little bit about the updating rule here. So this is shift towards right, towards left. This multiply by p, it's basically shifting every position towards left by 1, because the more towards left it is, the higher the power of p the digit has been raised to. So if we shifted the window towards left by 1, we have to multiply everyone by p, and we are getting rid of emit the old left. And this is adding the new right, and we do a modular to control to have the number relatively small. So let's see if it works now. Do we have an ANA? Yes. Yeah. So it's accepted. So this is the code for this problem. Really, conceptually, it's not too difficult to understand. This rolling hash. It's just a sort of like we have a vocabulary sized number system, and we want to convert that into decimal. To control the size of the decimal number, we do modular every place when we do the calculations. For the window update, it's looking like this. We shift the position towards left. We do a shift for all the characters. We get rid of the old one and we add the new one. Yeah, so that's this question today. It's pretty. I would say that June, this month's code problems is more difficult than the prior 2 months. I hope it's not the end of it. I feel that if the difficulty just keep going like this, the 2 remaining weeks can be quite challenging, and a lot of people are gonna drop out. So yeah, so that's the question today.